Now we will see some properties of these limits. So some very elementary properties that I will not get into the details here. So there is uniqueness of the limit in each case, in all these three cases. There is linearity, okay, and these inequalities, inequalities are preserved through these limit operations, okay. For instance, if, I don't know, xn converges to x almost surely and yn converges to y almost surely, with xn which is smaller than yn for all n, then the limit x will be smaller than y, okay. There are also some continuity properties, so it does not, I mean, it's not completely trivial here. So I will prove actually this. Actually, I will prove the almost sure one, and the convergence. I mean, the continuity for the convergence in probability will be optional. Okay, so I will do it now, but you can skip the video during the proof. Okay. So then also I leave the question open to whether, if you have convergence in LP and f is a continuous mapping, then f of xn, if xn converges to x in LP, then f of xn converges to f of x in LP. Okay, so that's an open question for you. So proof of this. So the first fact, almost sure convergence, as you will see, is not so difficult. Convergence in probability, it's a bit more tricky. Okay, so the first bullet point here, okay, is almost sure convergence. Okay, so remember that f is a continuous mapping. I'm working in R, say. So xn converges to x almost surely, that's the assumption. So there exists, let's say, omega star, a measurable set, such that p of omega star is equal to 1, and for all omega in omega star, xn of omega converges to x of omega. Okay, that's almost sure convergence, and well, here I will apply to this convergence here in R, that's a convergence in R, I will apply my function f, which is continuous on R. So since f is continuous, well, for any omega, so here somehow I fix omega, f of xn of omega converges to f of x of omega. Okay, so here what I've written is that f of xn converges almost surely to f of x. Okay, since this convergence, it happens on a set, on a measurable set, which has full measure here. So I have almost sure convergence, and that's it. Okay, so now that's where you can skip. You can stop watching the video here and continue later at the end of this proof. Okay, so I will prove convergence in probability. Okay, it's optional, so you can skip this part. Okay, so how do I do this? It's not very complicated. It's just it's not. I mean, okay, it's a typical probabilistic proof, but or analytic proof, but it might be skipped. It's not so important for the rest of the lecture. Okay, so so I will observe some things. So for any t and epsilon positive, okay, I will observe that. So I will make a set theoretic observations that f of xn minus f of x being greater than epsilon. Okay, so keep in mind that I want to prove that the probability of this event here goes to 0 as n goes to infinity. So for fixed epsilon, I want to prove that limit of p of this set goes to 0. Okay, so I will actually find sets in which this set is included. Okay, and actually I will work as an upper bound on these bigger sets. that I will exhibit now. So this I can write like this. So I will consider, actually what I want to use here is the uniform continuity. Uniform continuity will be much better to work with than continuity, but I am only assuming that f is continuous. And well, actually, if I want uniform continuity, I just need to work on a compact interval. Okay, so I will restrict myself to compact intervals, and here's how I do it. So somehow I will localize the problem. So I have f of xn minus f of x greater than epsilon, and here I will add a condition, which is that x, so the limit random variable is smaller than t, less or equal to t. But okay, if I do that, this is not an equality, so I need to add something. So I will add the same thing, f of xn minus f of x greater than epsilon, and here the complement of this event is x strictly smaller than t. Okay, so here that's not difficult to see that it is an equality, sorry. And here actually what I will do, okay, sorry, greater than t, of course. Okay, and here I will now use an inclusion. I will get rid of this part here. I will only retain this one. So you will see why after. So this is f of xn minus f of x greater than epsilon, and this I need to keep it for now, smaller than t. And here I will only remember that x is greater than t. Okay, so of course this set here is bigger than this one. Okay, this one, you can, when I put a comma here, you can see it as an intersection between this event and this event. Okay, so of course this one is bigger than this one, so altogether this one is bigger than this one. Okay, so that's a general inclusion that I will use. And now I will use the fact that if I evaluate f, okay, on the interval minus t, okay, actually it will not only be continuous but uniformly continuous. Okay, so since f is uniformly continuous on the interval minus t, then for any epsilon positive there exists delta positive such that for any x and y in minus t, if x minus y is smaller than delta, I'm only writing the uniform continuity, okay? This smaller than delta implies that f of x minus f of y is smaller than epsilon. Okay, that's uniform continuity. And so let's say okay, so now let's fix t positive, fix also epsilon positive. There exists delta, so delta is positive. I will choose it also smaller than t. So there exists delta between 0 and t such that, so I will use this inclusion here, okay, except that, okay, instead of t I will use t minus delta. Okay, here that was for any t positive, just consider that t minus delta is t. Okay, so I get okay, there exists delta in 0t such that okay, sorry, such that the uniform such that I should say star is verified. Okay, so delta is small enough, and I will get also that the set f of xn minus f of x greater than epsilon and when I look at x smaller, less or equal to t minus delta, here, this thing, okay, which corresponds here to this part here. So I'm considering this part and I'm seeing what happens here. This is included in, so consider this, okay. If f is uniformly continuous, okay, and this, say this is greater than epsilon. Okay, so here maybe I need to put less or equal here to be fine. So if this is greater than epsilon, and if xn and x are both in the interval minus t, then that means, okay, that means that this cannot happen. Okay, or this means, sorry, that x minus y, so xn minus x is greater than delta. Okay, that's the first possibility. But there is another possibility. Okay, it might happen that, so x, I know that it's in an interval minus tt because I have this condition here. But can it happen that xn is not in the interval minus tt? Yes, it can happen. Okay, but in that case, if it's not in the interval minus tt, I know, because of this condition, I know that the distance between xn and x will be greater than delta. Okay, so I consider that there were only two possible cases, and in both cases, the conclusion here from this, I mean, if I'm on this event, the conclusion is that the difference between xn and x is greater than delta in both cases. Okay, so I'm going to write this. So this implies that xn minus x is greater than delta, and I will also keep no, actually I will just write this. Okay, that will be enough. Okay, so this yields the following fx. So now I'm considering the whole event that I'm interested in, and I will include it. I will consider an inclusion in the sets that I've described so far. So I get that f of xn minus f of x greater than epsilon is included in, so remember there was this set, but this set is included in this one. So it's included in xn minus x greater than delta. And the second one that I needed is this one, x greater than t, or x greater than t. Okay. So remember, I want to prove that the probability of this one goes to 0. So the probability of this one is smaller than the sum of the probability of this one plus, okay, I will write it. So the probability that f of xn minus f of x greater than epsilon, this is lesser or equal to the probability that xn minus x is greater than delta, plus the probability that x, oh sorry, here it's t minus delta, by the way, x greater than t minus delta. Right. So I will need to prove that this one goes to 0, and this one actually does not depend on n, so it will not go to 0, but I can choose t as large as I want, so that this will be very, very small. Okay, so I can, like I said, first, if you look at the order of the way I choose the quantifiers, so at first I fix t, I fix epsilon, t and epsilon independently, and then I find delta, which is both related to t and to epsilon, so delta depends on t and epsilon. Okay, so what I will do is fix t, epsilon, t large enough so that this is very, very small, and then I will have my delta. Okay, I will have my delta, and for this delta it suffices to choose n very, very large, because I know that xn converges in probability to x, so this goes to 0. Okay, fine. So let me do this. So let's fix, I don't know, let's say I will fix eta positive, and let t positive such that the probability that x is greater than let's say yeah, the probability that x is greater than than t over 2, let's say, is less than eta. Okay, I'm not proving that I can find such a t, but you should check this. Okay, x is a real valued random variable, so I can find actually such a t. So check this. Okay, then let epsilon be, let's say, okay, let's maybe, yeah, let epsilon be fixed. Okay, I should prove the convergence for any epsilon anyway, so let epsilon here be fixed and choose delta in, let's say, 0 t over 2 satisfying star. Okay, well then by the convergence in probability of xn to x, there exists capital N such that for any n greater than capital N, the probability that xn minus x greater than delta, yes, is smaller than eta. Okay, hence we deduce from, so here I will call this double star. Okay, this inequality here, we deduce from double star that the probability that f of xn minus f of x being greater than epsilon, this is smaller. Okay, so here the first quantity is smaller than eta. The second one is also smaller than eta because we chose t large enough. So this is smaller than 2 eta. Okay, for all n greater than capital N. Okay, so eta is arbitrary. So we get the convergence. Okay, and that completes the proof. Okay, so now we will we will move to the metrizability of the convergence in probability. So I will show what I announced earlier, that there exists a distance. So it's not properly written as a distance here, but I can write it here if you wish. So I could call it dp. Okay, if I have two random variables x and y, and I define this quantity here, the expectation of x minus y divided by 1 plus x minus y. Okay, so you see that this quantity is well defined. Okay, this quantity here for any omega, this is less than 1. Okay, it's between 0 and 1, so it's not a problem to define this expectation. It's finite. Actually, it's a quantity that is between 0 and 1. You can check that it does define a distance, well, this distance on probability on random variable, sorry, well, it does characterize the convergence in probability. So let's show this fact. So proof. So so I have xn, which is a sequence of random variables. I will define yn, which is xn minus x. Okay, and I will prove that xn, instead of proving that xn converges to x, I will prove that yn converges to 0. Okay, so let's prove that yn converges in probability to 0 if and only if the limit as n goes to infinity of the expectation of yn divided by 1 plus the absolute value of yn. So if you wish, this is the distance, the one that I called dp before, between yn and 0, which also happens to be the distance between x and x. So I want to prove that this limit is 0. Okay, so first assume that yn goes to 0 in probability. So I will start with this assumption. So let epsilon be positive. Okay, remember what I know. So actually, so yn, I want to prove that this expectation goes to 0. So yn divided by 1 plus yn. This is equal. So here I want that somewhere appears the probability of, I want to get the event that yn, the absolute value of yn, is greater than epsilon. Okay, because I know that this quantity in probability, the probability of this event, sorry, goes to 0. So I want to see it appear somewhere. So I will introduce it. This quantity here is smaller than yn divided by 1 plus yn. Actually, I will start with an equality times the indicator function of yn greater than epsilon plus, well, the same thing, but this times it's times the indicator function of yn lesser or equal to epsilon. Okay. Well, now I have this inequality, so here it's the same. 1 plus yn indicator function of yn greater than epsilon. And here you see, if yn is smaller than epsilon, then this whole quantity is smaller than epsilon. Okay, so plus epsilon, and well, the indicator is always less than 1, so I bound this by epsilon and this by 1. Okay, so I just have epsilon in the end. Okay, and now you see I have this quantity here. So if I take expectations on both sides, I get that the expectation of yn divided by 1 plus yn is less than the expectation of, so here also what I can do is say that, I already said that, but this quantity is obviously smaller than 1. Okay, this is this is a divided by 1 plus a, if you wish, and so for any a which is non-negative, any real number which is non-negative, this quantity is smaller than 1. Okay, so actually this is also smaller than the indicator. I will just keep the indicator function here, so yn greater than epsilon plus epsilon. Okay, so that's less than the indicator function of yn smaller than greater than epsilon, plus, and the expectation of epsilon is just epsilon, so epsilon. Well, this, as you know, is equal to the probability that yn is greater than epsilon, and we know that this quantity goes to 0 as n goes to infinity. Okay, so and here epsilon is arbitrary. So the expectation of yn divided by 1 plus yn goes to 0. Okay, and now in the opposite direction, well, assume now that the expectation of yn divided by 1 plus yn goes to 0. Well, in that case, what I want to do is control, of course, is prove that the probability that yn greater than epsilon goes to 0. So I will fix epsilon. Okay, and observe that yn divided by 1 plus yn, but this is greater than yn 1 plus yn times the indicator function of yn greater than epsilon. Okay, so this is a trivial inequality. Okay, it's just saying that this is smaller than 1. Okay, this function is always smaller than 1. Okay, but here the point is that I'm introducing this this indicator function, and I know that when I take the expectation of this indicator function, I get the probability that I want. Okay, that I want to control. So if I mean, I need to say something about this, but yeah. Okay. Also observe something. Is okay, look at the function which maps y to y divided by 1 plus y. Okay, for y, say in r plus. Okay, this function is increasing. Okay, you can plot it if you want. It's a function that looks like this. Okay, it starts at 0 and it grows asymptotically to 1. Okay, so it's 1, that's 0, and that's your function. So it's an increasing function, and as such, we deduce that okay, this quantity here. So we know that yn is greater than epsilon, so this quantity will be greater than epsilon divided by 1 plus epsilon. Okay, so yeah, I will write it here, but that's really a consequence. So epsilon divided by 1 plus epsilon times the indicator function of yn greater than epsilon. We are almost finished here. Okay, I'm just pointing out the fact that it's increasing, I'm using this fact here. Okay, and now I can conclude. I will take expectations on both sides. So the expectation of yn divided by 1 plus yn is greater than, so epsilon times 1 plus epsilon, this is deterministic, this is just a scalar, so I can take it out of the integral. So this is greater than epsilon divided by 1 plus epsilon times the expectation of the indicator function of yn greater than epsilon. Okay, so this is equal to epsilon divided by 1 plus epsilon times the probability that yn is greater than epsilon. Okay, and now I can conclude. Why? Because well, this quantity, I know that it goes to 0. This quantity, of course, is non-negative, so it's smaller than something that goes to 0, so it goes to 0. Okay, so the probability that yn greater than epsilon goes to 0 as n goes to infinity. Okay, and we're done here. Good. Okay, so now what I will do, I will take a few minutes to compare the different kind of limits that we've introduced. So I've introduced convergence in almost sure convergence, convergence in LP, and convergence in probability. I want to be able to say, okay, if I have such convergence and it implies such convergence, is the reciprocal true also? Can I deduce? I mean, I want to be able to describe all these implications or not. Okay, so the first general result that we have is that if xn converges in LP to x, then xn converges in probability to x. Okay, and we have the same for almost sure convergence. Okay, almost sure convergence implies convergence in probability. Okay, I will discuss converse implications very soon. Okay, so let's first prove these two facts. Okay, so first LP. Okay, so that's LP convergence implies convergence in probability. Okay, so how do I do this? Well, that's just Markov's inequality. Okay, so just yep. So by Markov, so let's I want to prove convergence in probability. So the first thing to do is to fix epsilon. So let epsilon be positive. Okay, then by Markov's inequality. So what do I have? I want to control this. Remember, I want to prove that probability is that xn minus x greater than epsilon. This goes to 0. So I will say that this is the probability that xn minus x to the power p is greater than epsilon to the power p. Okay, these two things are exactly the same. Okay, and now I use Markov's inequality. So if you remember well, it goes like this. So expectation of xn minus x to the power p divided by epsilon to the power p. Okay, and this, so epsilon is fixed. I'm letting n go to infinity, and this by assumption goes to 0. Okay, so this goes to 0 as n goes to infinity. Okay, so it's very simple here. And now I want to prove that almost sure convergence implies convergence in probability. So again, I have two ways of proving convergence in probability now. I can either do it like this by fixing epsilon, or I can use also the distance that metrizes convergence in probability. So that's what I will do here. Okay, I will use this distance. So observe that xn minus x divided by 1 plus xn minus x is a random variable which is bounded by 1. Okay, so you probably see where I'm going. Okay, if I have a sequence of random variables that is bounded, and I know that this sequence of random variables, okay, look at it. What is this sequence of random variable? I have xn minus x. I know this quantity goes to 0 almost surely by assumption. So this also goes to 0 almost surely. So now, sorry, I take a function which turns out to be continuous. So consider if you wish the function f, which I've already presented this function to you earlier, namely here, this function here. So let's call it y now. Okay, 1 plus y. So this one defined on R plus is continuous on R plus. Okay. Or you can define it on R with the absolute value, maybe it's better. So it's continuous on R. So, okay, I've said previously that if I have a sequence of random variables that converges almost surely, then f of this sequence converges to f of the limit. So f of xn minus x divided by 1 plus xn minus x. Oops, sorry. Actually, it's just f of xn minus x. This quantity here, well, it converges to f of 0, okay, as n goes to infinity. This convergence is almost sure, okay, and f of 0 is equal to 0. Okay, so I have a sequence of random variables here, which is bounded by 1 and which converges to 0. So I guess now that you have it, I will apply the dominated convergence theorem. So by the dominated convergence theorem, the expectation, sorry, the limit as n goes to infinity of the expectation of xn minus x divided by 1 plus xn minus x converges to, I'm sorry, is equal to what? To the expectation of the limit, and we've said that the limit is 0, so it is 0. Okay, and so this, remember that this is dp of xn x. Okay, so by the previous result, we deduced that xn converges to x in probability. Okay. So I have a few more results for you, which I will not prove. So the first one, you can find the proof in the lecture notes of Le Gall. So it tells you the following: if so, it's partial reciprocal to the previous implication. This is very partial. So if you have a convergence in probabilities, then this implies that there exists a subsequence which converges almost surely. Okay, so it's kind of weak, and you can find the proof. Okay, so proof. Maybe I can tell you also that the proof relies on Borel-Cantelli's lemma, which you might have heard of, but that we will not discuss. So the proof is admitted. It relies on Borel-Cantelli's lemma. Okay, so see Legal's lecture notes if you want to look at this. Right. The second point is that if xn converges in probability to x, and if there exists a random variable y, which is in LP, such that yn is dominated by y for any n, then well, you have two things. First, x is in LP, and xn converges to x in LP. Okay. So I will prove this one. Actually, it's a nice consequence of the previous results. So again, it's a partial reciprocal to the sorry, to the previous result. We told you that convergence in LP implies convergence in probability. Okay. So let's prove this. So it's clear that for any n, xn is in LP. Okay, I'm using the domination here. What you should prove as an exercise, I give you this as an exercise, proof exercise. Okay, there is no quiz today, so maybe you can practice with this exercise. Prove that x is in LP. Okay, so the limit in probability with this set of assumptions will be in LP. And now I will use the previous result. So let's yeah. So by the previous result, so we know that xn converges in probability to x. So so it was theorem 1.7. There exists phi from n to n, which is increasing, strictly increasing, such that x phi of n converges to x almost surely. Okay, that's a result of the previous theorem. And then by the dominated convergence theorem, because I know that x phi n is dominated by y, then x phi of n converges to x in LP this time. Okay, that's by dominated convergence theorem. So any subsequence of any subsequence, actually I don't need to consider a subsequence, but any subsequence of x has a subsequence, so a further subsequence that converges to x in LP. Okay, so x itself converges to, so xn, sorry, itself converges to x in LP. Okay, that's the usual criterion. If you have a sequence and that any subsequence of this sequence has a further subsequence that converges, then the whole sequence converge. Okay, that's a classical characterization of convergence in any metric space, actually. Okay, so xn converges to x in LP. Right? So let me draw a picture now about all these kind of convergences. So okay, I have let's say convergence in probability here. I have okay, maybe a bit. Let's say I have convergence in probability here. I have convergence in LP here, let's say for some p greater or equal to 1. And I have convergence almost surely here. Okay. That's my three kinds of convergences. So I've told you already that there will be a fourth kind of convergence here. Okay. So I will discuss this later. But what we know is that almost sure convergence implies convergence in probabilities at theorem 1.6. Okay. We also know by the same theorem that LP convergence implies convergence in probability. Again. Then we had some partial results. So maybe I will change color here. So I have convergence in probability that implies almost sure convergence up to taking a subsequence. Okay. So here also I will have a partial converse. So it's partial results, partial results. Let's say that's okay, I don't remember the number. It was 1.7, I think. Yes. Okay. And here the converse was partial. It was theorem 1.8. Okay. And then I will give you counterexamples. So I will tell you that this is wrong in general. So that will be my first counterexample. Okay, so I will number them. So that will be the number 1. Then I will give you another counterexample. So this one is wrong also. That will be example 2. Then that almost sure convergence does not imply LP convergence. That will be my third example. That LP convergence does not imply almost sure convergence. That would be my example 4. Okay, and then later on we will discuss what is related to this fourth kind of convergence, but that's for later. Okay, so so let's say examples. Yeah. So the first one. So remember, I want to prove that I want to find an example of a sequence which converges in probability but not almost sure. So I will give you such an example. So consider xn, which is a random variable, a Bernoulli random variable with parameter 1 over n. And for each n, I take independent random variables, a family of independent random variables. Okay, so in particular, what I mean here is that the probability of xn being equal to 1 is equal to 1 over n. Okay, so the probability, of course, that xn is equal to 0 is equal to 1 minus 1 over n. Okay, so I will fix epsilon. So we'll choose epsilon in 0, 1, open. And the probability is that, so here I guess that the limit should be 0, okay, because it's more and more likely that xn will be equal to 0. So if there is such a limit in probability, I guess that it will be 0. So I'm computing this, so minus 0 if you like, greater than epsilon. Well, this probability here, okay, remember this is either 1 or 0. If this is 0, well, of course, this is not satisfied. So the only possibility here is that xn is equal to 1. So this is equal to the probability that xn is equal to 1, which, okay, as I said, is 1 over n. So it goes to 0 as n goes to infinity. So indeed, xn goes to 0 in probability. I will not prove the converse. I will just give it to you. Not the converse. I mean, sorry. I will not prove the almost sure convergence. I will leave it to you as an exercise. So prove that Xn does not converge almost surely. Okay. So now, how can you should think about this? If it does converge, it will have to converge to 0, okay? Because if it converges almost surely to some limit, then it also converges in probability. And since we know that the convergence in probability is towards 0, then the almost sure limit, if it exists, has to be 0 as well. Okay. So what you can do is prove that the Xn does not converge to 0. Okay. If it does not converge to 0, well, that means that okay, what you can try to prove is, okay, the contraposition of this, which is that for any n, an integer, okay, there exists n greater than capital N, such that Xn is equal to 1. Okay, if you take the contrapositive statement of this event, you will get that this is indeed the convergence to 0. Okay, so you look at this event. Okay, you try to do some computations. You try to, in particular, find a lower bound. Okay, and this lower bound, you try to prove that it converges to 1. Okay, so in particular, this means that this converges to 1, which is exactly saying that Xn does not converge, almost surely. Okay, so you can try this. So let's now look at the second example. So we want a sequence which converges in probability but not in LP. Okay, so let's try this. So I suggest you consider sequence Xn of independent random variables such that the probability that Xn is equal to, so again, I will take a sequence which can only have 2 values. So it can be 0 with probability, so very big probability, very close to 1. Okay, and the probability that Xn is equal to, so this time I will not choose 1, I will choose a very large value so that I'm messing up with convergence in LP, because it will take very, very large values, very, very rarely, and more rarely actually, but still very big values. Okay, so if I take, let's say, n to the 3, and with probability 1 over n squared, okay, then so I will show convergence in probability. Then for epsilon positive, or actually I just need epsilon, yeah, small enough, let's say. Yeah. What I get is that, so again, I'm guessing that in probability the convergence will be to 0. Okay. Well, again, if epsilon is not too big, or if n is large enough, if you prefer, then this is exactly the same as the probability that Xn is equal to n to the 3, which is 1 over n squared, so it goes to 0 quite easily. Okay, and now we'll prove that it does not converge in LP. So for this, actually, I just need to prove that the LP norm of Xn goes to infinity. Okay, it suffices to, okay, so to prove that Xn does not converge in LP, it suffices to prove that expectation of Xn to the power p goes to infinity. Okay, so the reason is because you know that if Xn converges to some x in LP, then I've said before that it implies that the expectation of Xn to the power p converges to the expectation of x to the power p. But if I know that the expectation of xn to the power p converges to plus infinity, that would mean that the expectation of x to the power p is equal also to plus infinity. So x would not be in LP, so I cannot have LP convergence in. Okay, it's just by definition. So I just need to compute the expectation of xn to the power p, and so it goes like this. This is equal to, so here it's quite simple to compute. So it takes only two values, so 0, so I don't care about 0, and n to the power 3. Okay, so then it's power p, so n to the power 3p with probability 1 over n squared. Okay, so this is, well, this is not, I do not need to discuss this because p is greater than 1. Okay, so it goes to plus infinity because p is greater than 1. Okay, so I don't have convergence in LP. My third example is, okay, you run a sequence which converges almost surely, but not in LP. Okay, let's go for this. So actually I can take the same example. So exercise again. Exercise proves that the sequence of 2 converges almost surely. Okay, this is kind of the same. You can do it similarly to what I've said here to prove that it does not converge to 0. Here you can do a similar. If you manage to find some computations here, you can more or less do the same. Sorry, you can more or less do the same here to prove that the sequence in 2 converges almost surely. Okay, it converges almost surely, and as we said, it does not converge in LP. So same example works. Okay, let's go for, okay, now an example of a sequence which converges in LP but not almost surely. Okay, but well, here same example as in 1. So you see I can choose quite easily some sequences. It's no need to go for difficult or complicated examples. So yeah, it's the same as in 1. You can check indeed if you wish. So in 1 I didn't prove it, but I said it does not converge more surely. The convergence in LP is easy here. It will be to 0. So xn minus 0 to the power p. This is equal, sorry, to, so remember in 1, the example, it only took, it's a binary random variable. So it takes the value 1. So it's 1 to the power p. And the probability that it's 1 is 1 over n. Okay, so it does go to 0 as n goes to infinity. So I have convergence in LP towards 0. Okay. So I will conclude this part with the strong law of large numbers. So that's the first important theorem of this lecture. The second one will be the central limit theorem. And you will see that we will be able to prove a weakened version. The general version, which we call the strong law of large number, it goes really beyond the scope of this course. Okay, so we would need advanced techniques, advanced martingales, what we call martingales technique. So I will present very briefly martingales next time, but very briefly and not with enough details so as to understand this proof. Okay, so I will not prove in full generality this theorem, sorry. But you need to know it and to know the assumptions. Okay, it's really one of the fundamental theorems of probability, and it has many many variants, but this one is the usual one. Okay, so you assume that you have a sequence xn of IID, what we call IID random variables. So IID stands for independent and identically distributed. And well, you have the equivalence between these two statements. Okay, I will comment on this after, but we have convergence almost surely of what we call the empirical mean. Okay, so you have your observations xk. You take the sum up to n of the first, so the first n observations xk. You divide by n, so you make an average. Okay, so that's why we call it the empirical mean. And if this converges almost surely to some value mu in R, okay, I'm talking about R, real valued random variable. It works also in RT. Okay, but if I have this convergence almost surely, then I can deduce that actually the xk's, which have the same law, have a finite first moment. Okay, they have finite expectation, and in this case, this mu here has to be the expectation of xk. So here you see that the choice of k is not important because they all have the same law. Okay, so it can be x1, x2, anything. Okay. More usually it's read the other way around. That is, if the first moment is finite, then I will deduce this convergence here. That's usually how we apply it. Okay, so if I have an IID sequence with finite first moment, then I have almost sure convergence here of the empirical mean. Okay, so that's the empirical mean which converges to the actual mean. Okay. So the fact that I call this the strong law of large number, it refers to the fact that here that's an almost sure convergence. So that there are alternative statements of the law of large number. So this is what I just said, and here is one. Sometimes you find it written like this. So assume that still, so you have the IID assumption as well. And this time you assume that it has finite second moment. So it's a stronger assumption, okay, which is not necessary, since we have seen that necessary and sufficient condition is that the first finite moment is finite. The first moment is finite, sorry. So here you assume something a bit stronger. And in this case, again, of course, you get the almost sure convergence. Okay, so that's an alternative statement that you might find. What happens also if you ask for the second moment to be finite, so the variance to be finite, is that you get also a convergence in L2. Okay, remember that convergence in L2 is not equivalent or not weaker nor stronger than the convergence, than the almost sure convergence. So that's an additional information if you have finite second moments. Okay, so actually that's this convergence in L2 that we will prove. Okay. Because it's easier. The almost sure convergence is not within our reach. Okay. So okay, so let's prove. So we will prove. So that usually when we prove only the L2 convergence or the convergence in probability, because it will imply convergence in probability. That's what we call the weak law of large numbers. Okay, so we prove only the convergence in L2. And like I said, almost sure convergence is a bit too difficult. So we prove only the convergence in L2. Okay, which in turns implies convergence in probability. Okay, and when we have convergence in probability, this is referred to as weak law of large numbers. So how do we do this? So well, I compute it. So expectation, I compute the L2 norm basically. So the expectation of 1 over n times the sum of the xk's for k equal 1 to n minus, so mu, okay, because I want to prove convergence to mu squared. This I will put it slightly differently. I will put the mu inside the sum, so that the expectation of 1 over n times the sum for k equals 1 to n of xk minus mu squared. Okay, so it's just a small algebraic trick. And now I will expand this square here using the independence. Okay, so here that's 1 over n squared. It's not difficult. Sum for k equals 1 to n times sum for j equals 1 to n. Okay, so I'm developing the square of xk minus mu times xj minus mu. And of course, there's an expectation here. Okay, so before this, the sum was inside the expectation. That's a finite sum. Okay, so now I take it outside the expectation. Okay, and I know that this expectation here, is equal to 0. Okay, this is equal. Sorry. This is equal to the product of the expectations, so xk minus mu times the expectation of xj minus mu if k is different from j, and this is equal to, of course, expectation of xk minus mu squared if k equals j. Okay, but the first one here, okay, this is equal to 0 because the expectation of xj is mu. Okay, so the first line is if k is different from j, this is 0, and the second line here, well, this is the variance. This is what we called sigma squared. Okay, so altogether this is equal to sigma squared over n. Okay, so it goes to 0 as n goes to infinity. So we have L2 convergence in probability, so this part is quite simple. Okay, so I stop here. I do not prove anything more. Okay, and to close this part, just a nice application of a numerical application of the law of large number. Actually, that's what we call simple example of what we call a Monte Carlo method. That's a very rich and powerful area of probability in mathematics. So it goes as follows. Basically, you have an analytic object, like an integral, and you want to approximate it numerically. So what you can do is, so let's say, okay, that's a function here, which is integrable over some interval, say 0, 1. Okay, so I want to approximate this quantity. I cannot do it analytically, maybe, I don't know. F might be a bit complicated. So what I will do is, first, I will write the transfer theorem. So I will introduce U, a uniform random variable over 0, 1. And so I use the transfer principle to say that the probability that U is in B, okay, B is some Borel set of R, or R plus. Okay, F is valued in R plus. So if I look at this quantity by the transfer theorem, this is given by this integral. Okay, so the integral over B of the indicator function of 0, 1, because this is the density of the uniform random variable. And the expectation of f of u, well, it's precisely the integral of f of x times the indicator function on 0, 1 integrated against lambda of dx. So this integral, okay, is exactly the expectation of this function. Okay, so what can I do now? Well, I choose, or if you want, I draw a sequence of IID random variables, which are all uniform random variables on 0, 1. And now the strong law of large numbers tells me that the limit of the 1 over n times the sum of the f of ui's, it converges almost surely to this expectation, the expectation of f of u. Okay, and as I said before, this expectation is precisely this integral. So what I'm saying here is that if I draw independent, finite number of independent uniform random variables on 0, 1, okay, I take, so I look at the value of f of ui. I average all these values up to the number of samples that I've drawn, which is, say, fixed capital N. Well, this empirical mean, this average, it approximates this integral. Okay, so I have a way to approximate this integral numerically, say. Okay, so of course here there's something probably missing, is you want to know what error you are doing when you do this. Also, you know other methods to approach numerically, to approximate numerically this integral. So you want to compare it to other methods. Usually, these kinds of methods, Monte Carlo methods, are very efficient when the problem is high dimensional. Okay, Here, when you're in R, it's maybe not so efficient, but if f is in RD, then usual deterministic numerical methods might be quite computationally intensive, and Monte Carlo method can be interesting. Okay, so one thing that is missing is, and that will introduce the last part of this lecture, is to compare, to be able to say what error you're doing between the finite sum here, so the finite sum approximation, and the true value. And this can be quantified thanks to the central limit theorem.